Hello. Uh, Today I'd like to talk about um, camera model. This is a series of the lecture in digital image processing. This is lecture number 10. Previously, I talked about perspective. In lecture 9, I talked about perspective. Before going to the stereo image, stereoscope image, I would like to talk about camera model. So this is about camera model. Previously, I talked about the uh, about this transformation and perspective and also translation, rotation, and um, scaling. I talk about that, and perspective transformation. I talk about that. And today I would like to talk about camera model. And here, the camera model equation 23, 24. Let me bring these two equation that I previously I told you. These two equation about the homogeneous and perspective coordinates and perspective transformation. Uh, 23 and 24 is this. And back to the Cartesian coordinate and so on. Equation 23, 24 characterizes the formation of an image by projection of three dimension points onto the image plane. In this case, we think that the image plane coordinate and world coordinate are separate. In the sense, uh, uh, the figure 28 here in this figure, we have the world coordinate here, x, large y, large z, and camera coordinate, which is x0, y0, z0 here, xyz or small xyz, and this not they are not corresponding. These two, I mean, coordinate. The coordinates x, y, z used to locate both the camera 3D, denoted by W. Figure 2.80 also shows the camera coordinate x, y, z, and image points denoted as C. Here, the assumption is that the camera is mounted on a gimbal, and this is gimbal, where its gimbal is here, is not here, and we have R here, the distance, the vector R here. So everything should be used for translation and rotation and everything. There are some which allows pan through an angle theta and tilt through angle alpha. Pan is the angle between axis x, small x and large x's, and tilt is the angle between the small z and large z. The offset of the center of the gimbal from the origin of the world coordinates system is denoted W0. And the offset of the center image plane respect to the image coordinate center is denoted as yes, as R, with the R1, R2, R3. Let me show the, maybe it's better here also. I can use the, okay. Here is R1, R2, R3. Okay, back to here. The concepts developed in 251, they provide the necessary tools, and the figure 28, the arrangement, geometric arrangement 28, and so on. We want to bring the camera world coordinate into the picture coordinate, photo coordinates, aligned with the application of theta transformation. After denoting the simple perspective transformation, which is 2.22, I have to show this perspective. This one. This is the perspective transformation. Lambda is the focal distance of the camera to obtain the image plane coordinate and so on. And so they suppose that the initial normal position since the gimbal center and so on. And let me show the formula here. I don't want to go into detail. The uh, figure 27, let me see here, 27. Yeah, it's back there. Okay, yeah, is the coordinate, image coordinate and so on. And this I told you. The translation, we use three translation, transformation for alignment of the world coordinate and camera coordinate. What is this translate transformation? Which one is translation? Let me see here. One is translation of the original or filter coordinate to the location of gimbal center by using transformation this G 1, 1, 1. This is 4 by 4 minus x0 minus y0 minus z0. In order towards the homogeneous word point WH that was coordinate x0, y0, z0 is obtained a new coordinate as GWZ. So multiplying G and W, the homogeneous coordinate of the world, WH, I told you what is homogeneous. So we can translate this. Also, we have two other rotation here between x-axis and z-axis here, theta, and z-axis, which is r theta, and r alpha, which is totally is for z-axis is alpha, which is r alpha. So we have two matrices. R is r alpha multiplied by r theta. Imagine the matrix multiplication should be in order. So R theta, G, W, and H, and R alpha, R theta, G, W, H. So totally, I don't want to read all of this story in book. So you can use it. You can later see the book and read that. So R is this. After two rotation matrix transformation, multiplication of the two matrix is cosine theta, sine theta, and so on. This equation 39. And finally, the displacement of the origin of the image plane by vector R achieved by this. So we have another R. I told you the R was here. This is R. So we have to translate R also. So this is the another one. So it is another one was G, another was, you see, this is G. First was G right here. Here it was G, and another is a C here, the translation G, a C. So totally, in order to match these two coordinate is CRGWH. Then you find the camera coordinate system into the distance. Bring the world and the camera coordinate system into coincidence. The image plane coordinates point WH are finally obtained from equation 23. Previously, I told you, in other words, the homogeneous fourth point is being view of by camera satisfy the geometric arrangement and 2.18 in figure that I show you. So totally is the image coordinate is CH in homogeneous coordinate is P perspective, C translation, R double rotation, G translation over WH the world coordinates in homogeneous. So equation these 41 represent the perspective transformation involve two coordinates system. That's why it become more complicated. It's a C perspective, but it is more complicated because we have two translation, rotation, and other translation, rotation, and the other one, and perspective, of course. So after this calculation, if you multiply all these metrics, you obtain the image coordinate x, which is this, and y, which is this. So in simple case, if they are match, and if they are matched, then you will see that you will reduce to the same equation previously I told you, very simple equation, if they are matched. Now we assume it is not matched. So in this case, when x0, y0 is 0, r1, r0, and alpha theta, this equation 18 and equation 18, 19. This equation reduced to 18, 19. Let me show you 18, 19. You will see. Oh, of these two. These two equation, if everything is set, so it is just two uh, three dimension, and this is the image coordinate, this is the board coordinate. But we have also z, which is missing distance. That is in a serious. So for this is camera calibration and camera model. So here I just explained this, and one example is here. And alpha theta is 0, reduced to this, okay? Example as an installation concept, just discuss, suppose that we want to find the image coordinate of the corner of the block shown in figure 2.19. The camera is offset from the image and 128 till 125, and transformation and counterclockwise viewing the original. Anyway, after this calculation, and anyway, this picture that I don't want to show you all of this, you have to calculate this, all of these images. Then the following parameter value apply to this problem. X0 is 0 meter, Y0 is 0 meter. It is a world coordinate. But Z0 is 1 meter far from the camera. And alpha, tilt, and one is tilt, one is the other one. This two, I should tell you. Between X is tilt, and Yes, between x, we suppose, and we between alpha. Alpha is between z. The axis z is alpha. That is the tilt. That is tilt. The other one is pan. That one is pan. Between x is pan, and between z is tilt. Anyway, you can read here. Since tilt is between the two axes, alpha, and then so on, and r theta is pan. Okay, let me return because it takes time here. Okay, so alpha theta are 135 degree, and R1, that is simply a gimbal point. Gimbal. This is gimbal from the standing, and gimbal. Here is R. So R very small, not so big. This is exact, in exact case. Something like the exact case. 0.03 meter, which is only 3 centimeter. R2, R3 is 2 centimeter, and lambda is 35 millimeter. Or millimeter, or 0.035 meter. So after putting this to the equation, the computation image coordinate of the block corner, we simply substitute the parameter value to equation 45, 43, and we obtain x like this and y like this. If lambda is this, so x is 0.0007 meter, which is 0.7 millimeter, and y of the image is 9 millimeter, maybe something like this. So it is image on image plane, I mean. Finally, note that the coordinates simply 24, 45, 43, with location 45, 43, or with respect to the center of the image, a change of the coordinate is required to use a convention established earlier, that origin of an image is its top left corner. Okay, that doesn't matter. It just we wanted to make a this camera calibration, no problem. It's camera model. Camera, we wanted to make if the world coordinate and the camera coordinate, world coordinate and camera coordinate are not, these two coordinates are not aligned just by W0, R, and 2, tilt and pan between X and X, X, pan and tilt between Z, small z, and large Z, which is this. Between this and this, which is tilt. After this translation, rotation, and so on, we can match this coordinate to this coordinate, and we obtain from a world coordinate, we can obtain C, which is image coordinate, exactly on image in millimeter, because this is in meter, it's just in the world, and this is in meter. After matching this coordinate, small x, y, z, to bring into x, y, z. This is the, for this is enough this here. Later, I will tell you, because this is necessary for this camera model, making these two coordinate match. Then we go to the, I mean, we go to the our model here. Again, I show you. This is G, this is R, this is transformation again, C, and this is other images that I didn't show you. And then after this, we can obtain X, Y. Here I didn't write. Anyway, after this, we go to a stereo image. A stereo image means that if you have two camera, like two eyes, human eyes, then you can find the, calculate the Z. Here just we match the two coordinates, but we miss the missing. This is missing depths. In single camera, you cannot find where is W, how far is W, and then you just you measure the XY or XY. But if you have two X1, Y1, and X2, two, then you can find the missing depths of the W, which is the how far the distance is this. This is especially important in robotics, which robot should estimate the obstacle, the distance of obstacle from the camera, and then from the robot, and then estimate it, and in order to avoid collision and so on. This is a stereoscope. You can also use missing depths from speed of the vehicle, and by single camera. If you know the speed of the vehicle, you can find the missing depths, the front, for instance, one car here, one car in front of you, in order to avoid collision by knowing your um, speed and on two speed of two cars, then you can estimate the W by single camera. And this is the talk of the stereo image of the next section, number 11. This is number 10 here, finish. Is camera model here. Our model was here. So I stop here and thank you very much.